as I said, jump into using Excel. I mean, there's plenty of tutorials and stuff you can find with a simple Google. This is one I thought was okay. It was one of the first hits. But let me bring Excel here. Oh. Yeah, sorry, this is, where did I get that from? Sorry, first let me share. Yeah, who was it? I think Kyle or whoever was talking about the housing prices in New Jersey. This is something that is not exactly that, but this is government data about taxes. There's county taxes, citizens taxes. This has how many points? Yeah, 500 something. But you might be more interested in this one, the municipal tax summary. So this is all data from New Jersey. I need to find the here. This is just from newjersey.gov. You could probably extrapolate some stuff from this, especially about, there's a relationship between taxes on a house and the price of the house. Your house gets more expensive, you pay more taxes. And in any case, this looks to be, fairly complete. On the website there's more data than just this. This is just one that I picked out that I thought was kind of sort of close, if you're interested in New Jersey in particular. Okay. Where's my other Excel here? I think I need to share this. Oh, can you guys see this this other Excel sheet? It's just empty now. Yes. Okay, thank you. Okay, so I'm assuming that you guys all have Excel. I don't think you can use Google Sheets for this. If you don't have Excel, I believe you should be able to download it through either the Rutgers software portal or through Office 365. If you have, I think you guys should all have an Office 365 email address. Yeah, the other option is Python, but maybe we'll skip that now. If you're particularly interested in Python, talk to me offline, and I'll give you a few resources for this. Maybe an extra lecture, or not like a whole lecture, like an hour talk or something. But it sounds like for most of you guys, Excel will be fine. All right. So once you have Excel, there's a few things that you need to do to set things up. It's pretty easy. There's something called an analysis tool pack that you don't have by default. it's already installed, it's just not turned on. So you have to go to File, Options, Add-ins, and yeah, it should be Excel add-ins here to go. And then by default, this is not packed or not checked. You just check it, the analysis tool pack. Don't bother with the VBA one. That's Visual Basic stuff. You don't need that. After that, click OK, and you'll have this tool pack. Now you can do linear regression in Excel. So let me find, well, I'll just do this. X, Y, I'll just make it real simple to start, and then we can make it a little bit more complicated. Whatever. Okay. So here you have these data columns, and I'd like to graph this. Yeah, I'd really like to graph it before doing the analysis. Let's see. Right. So for here, I think you need to select the column headers as well. And then in the Data tab, where is scatterplot? Sorting or filter. Oh, I'm sorry. Insert. Here. Insert, charts, scatter. Okay, there. Now we have all of our points graphed out. So again, this isn't something you have to do. Excel just does it very quickly, and that's pretty easy. Let's see. Right. Here, so by this picture, there's a little plus. For this trend line, you can fit a linear trend line. Exponential. These are all linear regression, okay? Linear forecast. Actually, the moving average isn't. But now you've drawn the trend line. So that's the best fit line. That's found by minimizing the sum of squares. That's an okay way to think about it for this. Now, for the toolkit thing, then you can get more information than just this. This is fine for drawing a line, and you can look at it, but you don't get a lot of information from it, especially things like the slope, the intercept, all of these things. So in order to do that, you go to the Data tab, and that's not it. Here, Data Analysis. So this is what was added when you did the analysis toolkit. Okay, here you have a bunch of options. We're going to be choosing regression. Okay, you need the Y range. So here, B to colon dollar B $6. I think that's it. No, second dollar. 6. Okay. Input X range, almost the same, except that's from column A. Okay, we'll give labels. Sure. Residual is another word for error. Okay, so sometimes the mean squared error is sort of the mean squared residual. Residual is just a word that statisticians prefer. I tend to just use the word error because I come from a different background. Okay, and that should be it. And there we go. And that's it. There, now you've done linear regression and you're done. Okay, I don't think for whatever data that you guys are going to be working on, the Excel part is going to be that difficult. There's some numbers here to know about. I haven't defined this score, the R square. I'll give a definition of that after I close down Excel. But basically, R squared is a way to measure how good of a predictor the X is for the Y. So if when X goes up, Y also goes up. If it's a very good predictor, this will be a number that's close to 1. If there's no relationship and, you know, it's just a flat line with points all around it, and so you predict nothing, then you're going to get a number that's closer to 0. Here, the standard error, this is just the summed residuals, the summed errors. Yeah, this p-value is also something I'll talk about next week. Very quickly, a p-value is for calculating a confidence interval. It tries to compare your predictor. Your predictor here is the line, because then now for points that you haven't seen, you're going to predict things based on, you know, what's the x coordinate and where is that on the y line. how good is your predictor versus something that's just totally random. So here, the smaller the p-value, the better. Here you see the slope and the intercept. And down here, this is just the detailed what your line predicted and how big of an error there was. If you sum all these up, take the absolute value, that should be the standard error. And here, SS, that's sum of squares. So if you square the regression, or if you square the error and sum it up, then that's this, SS. Yeah, this is just the errors. Again, the squared sum, and fine. That's about everything that you need to know now. So let me stop for a minute and check in. Does this seem manageable for you to do in Excel?
Yeah, that seems pretty easy, but I'm just confused as to how you would do it with something like that has multiple dimensions.
Yes. Let me think. I was going to show this next week. Let's see. Is that something, Brian, that you'd want to see today? It's fine, I can do this. It's just I'll have to readjust sort of what my plan was for teaching today, but that's okay.
I don't necessarily mind. I don't. Yeah.
Okay. Let me see if I can do this simply. Yeah. Yeah, see, this is okay. Well, if we do this, we'll do it after this next break. Okay. Until then, are there any other questions about this? I'm going to do one more example using the same 2D points, but on a larger data set. Nothing super crazy, but anyway, I'll go through all of it again just so you see it again and see it on something that's a little bit more significant than this. Okay. Let's see. So I'm trying to download this data set from Kaggle. All right, let's just open up Excel. Okay, you guys can still see the screen? Now with more data points? Okay, great. So this is still not super big, but it's got like 700 data points. And basically all I'm going to be doing is showing you that with 700 data points, I mean, before it was 5, now it's 700, it's still going to go like that. So if you have, you know, a few thousands or I can try something like 1,000,000 data points, but I'm not exactly sure what the best way is to generate data here. Oh, not saving anything. Okay, so you only need to do that toolkit thing one time. After that, it's available to you. So we can highlight our data, go to draw, no, not draw, insert, scatter, and there you go. no time at all. Like Excel is really, this is like small data. Okay, and if you're so inclined, you can add a trend line. This is a linear trend line. You'll notice it adjusts the scale some. Here, the best fit lines is going to be y equals x. Okay, that's how this data was generated. And then for the linear regression part, go to data, data analysis, regression. Now we'll need to adjust these. This is going, we want it to be 700, and that's A1 to A700. We want residuals, we want labels. Fine. What's wrong with the input ranges? Do this. Odd. What's wrong with my ranges? Sorry, I am no Excel guru. I prefer Python. 701. Yeah, what's wrong with this? By the way, if you guys are more familiar with Excel and you have a more efficient way for me to do something, I would love to hear it. Columns A and B, yeah, no problem. So stupid. Oh boy. I don't see anything wrong with this the first time. Let me see, maybe, is this missing? No, it has an X and Y, as it should. Well, that is easier than typing it. What? No. A, B. Is there a minus here? Heck. Oh man, I'm sorry, guys. I hate wasting your time like this. This is really, really dumb. No way. Sorry, I just don't believe it. Can't believe that that's more numbers than Excel can handle. I don't believe it. That would be too crazy. So that's fine. So I'm doing the stupidest thing in the world right now. I'm just trying to debug this thing. I can't believe that 700 points is too many for Excel. Like that's crazy. Okay, let me look into this, because if this is a problem for Excel, that could be a problem for what I was thinking. I thought. So okay, guys, let's take a 10-minute break. Let's make it 15 minutes. I will continue to figure out what the problem is with these points and try to show something in 3D that I believe that Excel should be able to do. If not, that itself would be a real shame. Okay, so let's come back at 8:15. Thanks. Pause. Good, well, at least it wasn't recording me doing that. I'll do it one more time for the sake of the recording. So I've now just made 2,050 points with regression. And if you go to data analysis, regression, there's over 2,000 points, and it's done. Okay, so here, I know one more thing I could do. Oh, God, I don't want to waste so much time. I won't do it on that big one because it takes me a long time to copy stuff. I forget who was asking about where are these blank? I really don't like Excel. Okay. Whatever. Let me take these three. Okay. So here, let's put. We'll call this x1 and x2. Okay. So this is going to be for a 3D thing. And this is, let's say, the price of something. Graphing it is something else. I don't know of a really nice way to do it in Excel, but if you can just graph things in 2D, that's probably okay. You just make different scatter plots for different columns. Always the Y is always the same column, and then the X, you have multiple graphs like this. But just to show you also how to compute the slopes of all of these things. Here, data, analysis, regression. So now the Y range is, let's say, the price. So we'll make that the C column now, right, where the Y is here. For the input X range, we actually put in 2 different columns. And like I said, I think you can go up to 16 columns, and then it's done. So here, instead of sorry, A1, sorry, just a minute. Great. Here on the left you have A, on the right you have B. So this means that that your Y is going to have to be your last column, because this is going to be a range of columns for the X's. So if you have like a Y column splitting up your X columns, I don't know how you input it into this. In any case, of course. Doesn't even have that many. Okay. Okay. Then here, you will see the same thing for r squared, except here instead of just, there's still one y-intercept, but now you have 2 slopes. One is the slope of y with respect to x1. The other is a slope of y with respect to x2. And each of those together, if you take these lines and project them out, that will create like a plane, like a sheet of paper. That's what a line looks like in 3D space. And in 2D space, a line is just a straight line. In 3D space, it becomes a plane. In 4D space, it's still called a plane. Just a 3-dimensional plane, 4-dimensional plane, 5-dimensional plane, etc. So that's how you would get the numbers, anyway, for this. Being able to picture it is something that's a little different. Yeah. If that's something that you really care about, let me know before next week so I can prepare something. Could I redo that? Oh, sure. Do this thing? Yeah. Just for fun, let me make it 4D. So let me go back to the sheet. Nope, this one. Okay. So here, you have to have all of your X things, all of the independent variables on together as columns. So here, I'll move this predictor now over. I'll put it out here, away from these. And now I'll call this x3, and I want to change these two. really dumb, but whatever. Okay. So now, let's say that here's the y that we want to predict. This is like the value. And this function here is going to have three things. So this function is going to look like y equals, I'll call it m1 x1 if I write an underscore, it means a subscript. So, you know, that's a straight line. But here, y depends on more than just x1. It also depends on x2. So this would be plus m2 x2 plus m3 times x3. So this is what the line is that this regression thing is going to be predicting. So this is going to be a line in now 4D space. So you have three x values and then a y value that's pointed up in some crazy place. And what this will be presenting to you is the intercept b, and we'll have three different slopes. Okay, so let's do it. Go to data, data analysis. Come on. What's the problem? Okay. Data analysis, regression. Here you put your range of y values. So there, those are my y values. Here, I guess, can you highlight this? Probably. Great. You can also just highlight it and it'll do it. But if you have like a lot of data, like 1,000 points, it's really annoying highlighting lots of columns. So here, this is the start column A. Why? Don't do that. And this is the end column, in this case C. So we're including A, column B, and column C. And we're doing the from rows 2 to 29, because row 1 is a title. Hit OK, and there you go. So we have one intercept and 1, 2, 3 slopes. Of course, this is a perfect line because I made the data in a really dumb way. I just wanted to do it quickly. Brian, does that answer your question? Do you follow it? Yeah, good. Okay. So like I said, the actual using Excel part should be pretty quick. You know, I mean, once you have data, load it into Excel, draw a couple scatter plots, do this thing, and it pops out with the answer for you. So what I'm more interested in is, one, I hope that you can actually apply this to something that you care about, because it will make it more interesting for you. And two, that you also leave yourself a little bit of time for some analysis. So talking about, not just giving, you know, these are the slopes that it gave me, but try to think about what does it mean for this to have this slope? So if it's buying a house, for every increase of 100 square feet, the house price is going to go up by $75,000. You know, even just saying that, just sort of rewording the meaning of the slope here is better than just giving a number. What else? Yeah, and like you're gonna write, some analysis, like things that you learn from this, things that you can tell from it. That can be in words and stuff. Okay. Yeah, sorry about the graphing component of it. I really think that there's something very good about trying to visualize data. Unfortunately, I think that Excel isn't really meant for data visualization. It can do a scatter plot and some bar charts and things like this, but not for like high dimensional data, or apparently even graphing in 3D is hard. What material do you like on the analysis? R squared? Yeah, that's part of it. I'll talk about R squared properly. It's very short, what there is to say about it. But yeah, like how much, how good of a predictor is your predictor? Your linear regression. I mean, that's what regression means, is to make a line that predicts. So, given the data that you worked with, how good was your line? Was it really good, or was it not so good? If you're especially dealing with your own data, where you're being a little bit more creative, things might not work. And that's okay. You don't have to, come up with a good predictor, so long you put in the work of trying to make a good predictor, and you can explain what you did and why things don't work. Other, a simple analysis breakdown. One, what is the y-intercept and what are the slopes? I mean, this isn't strict, okay? These are just suggestions of like things that would go good into like a basic analysis. Why are the slopes what they are? I.e., what do they mean? And I hope that that's not a difficult question. If it is, let me know a little bit in advance. Like if you're having trouble understanding something like why the slope is like this. 3, does linear regression work on this data? If yes, explain yourself. Sorry, if not, explain yourself. It's fine. Like, again, don't worry if things fail. If you do the right things and it's just not a good application for linear regression, I'm not going to hold that against you. 4, if there are more than one predictor, e.g. with housing, size, number of bathrooms, distance to transit, etc. Which of them were the most important? Which were the least? So if you're buying a house just in this running example, um, there's going to be many things that contribute to the price of a house. Some of them are going to be more important, some of them are going to be less important. You should be able to tell from your analysis, from looking at these things, which is the important ones and which are the not important ones. And that's it for a simple analysis. You don't have to go crazy with it. Okay. Okay, because r squared is so quick, I can cover that really quickly, and then at least that way you'll know what the r squared is here, because I've said it a few times. But before I do that, are there any other questions about this Excel stuff for now? Hopefully you've seen enough. I mean, I'd really like you to know enough to be able to start playing around this weekend. Maybe you can knock out the whole thing this weekend. I don't know. That'd be great. But, at least you've seen stuff. Seems like enough to start it. Okay. Who was it? Jake. Do you have a mic? You in front of your computer? That's fine. We'll talk about more of them. Jake, are you around?
Yes.
Good. Yes. So is this making a bit more sense now, at least with what to do with Excel and how to, I don't know, work with whatever data?
Yeah, I think the Excel data, putting all that in makes a lot more sense.
Okay, so you don't need to plan on drawing like a million graphs or anything.
Yeah, I got that now, and I forgot what the website was that you cited earlier in the comments. I think it was Kaggle.
Yeah.
So I think it makes a lot more sense now, to be honest.
Okay, good. All right, thank you. So yeah, basically, I was trying to leave room for the end of the semester to do some kind of project. We talked about it on Tuesday, like to start thinking about it. Hopefully, you have some data now, or if you don't, you'll be able to find it quickly. And I mean, I think so far we're on pace. I don't think you should feel really stressed out or like that things are coming under the wire. But, if it's like next Wednesday and you've done nothing, you might have a bad time. So I think we're making pretty okay progress through this. All right. So I won't get to everything about this analysis today. I'll talk about more of it the next time. There's a couple things that I do want to talk about. These I already have. So let me make these wider. Okay. This stuff at the bottom is the easiest. This is the number of data points you have. So for each data point, what did your line predict? and how far away was the real point from your line. So if it's not a perfect fit, if it's off by a little bit, by how much? That's all that this is. Not particularly useful unless maybe you're looking for an outlier, for example. So you might be able to, look at these residuals, and all of them should be kind of small. If one of them is like gigantic, then that might be a point to delete and retry. Retry doing your line fitting. The slope and the intercept, already talked about it. These things are not too bad, but I'm not going to talk about them right now. I'll save these for next week. The p-value and stuff, it requires a little bit more time. Like we could finish it in an hour, but in any case, for now you can forget about these. Okay? The significance, I don't know if I want to talk about these either. I don't know how important these things are, to be honest. At least for this class. This one you should definitely know, the sum of squares. It's pretty simple. It's just, you take all of the errors and you square them and add them together, and you get a number. Here are the number of observations. Here. So this is one thing that's annoying. I've tried to avoid it, but now that we're using Excel, there's more language, more jargon. Observations. Excel, these things are using terms that statisticians like. Economists will use different terms, mathematicians will use different terms, computer scientists will use different terms, and it's kind of annoying having to adjust things that you already know into other people's jargon. In any case, I'll introduce some more of this to you today, just so you're not confused. We have talked about a lot of this stuff. It's just, dependent variable, independent variable, observations, residuals. Like all of these things are just jargon for statistics. Residual is just error. Observation is just a data point. What else? Independent variable, these are the x's. These are anything that would go on the y-axis, or on the x-axis. The dependent variable is the y. So this is different than dependence and independence in probability. Here it just means that if y is a function of x, then when you change x, y also gets changed. So therefore, y is the dependent variable, and all of the x's, if you have more than one x, they should not play with each other. They should not be functions of each other. So these are independent, because they're independent of each other. Y is dependent on the combination of all the x's and stuff. So if you see independent variable, dependent variable, that's all it means. Okay. R. That's basically what all this is. The standard error That's just the absolute value of error, not the sum of squares, just the absolute value. Whatever. Okay. So let's talk about r squared. I'm going to turn off this, and r squared is very quick. After this, we can take a break and move on to better things in life. Okay. All right. I don't want to be. You want to be here? No. Let's go to linear regression. All right. So first, I'll just give the formula, which is very easy. Yep. Okay. Oh, now it changes. Okay. So definition, r squared. So this is, it's just an equation. R squared equals 1 minus the that's a good way to write this. So this is the sum of squares, the sum squared regression error over the total sum of error. Sum squared regression error. And this is the sum squared total error. Okay. Yeah. So in a more mathy way, 1 minus sum of yi minus yi hat, and I'll explain what the hats are and stuff, over the sum of yi minus y bar squared. So sums over I. Okay, so this is very easily seen by a quick example. Oh, let me add something else. R squared is a value between 0 and 1. If 0, it means that the regression line explains none of the data. And if 1, it means the regression line explains all of the data. So here, what do I mean by explain? A quick example will make it very easy to see. Okay, so here, by the way, y hat I is predicted y bar is the average y. Now here, you'll notice that y bar does not have an I. That's because y bar, this is the expectation. This is the average. So it's one number all the time. All right. Let's see. So here, if r squared equals 1, something that would look like that would be this. Right? Our regression line perfectly goes through all of the data points. So just to reiterate, this is the independent x. This is the dependent y. Okay. On the other extreme, r squared equals 0. What this looks like is this. For example. So this line has pretty much no relationship to these points. So that is what r squared 0 looks like. If you have an r squared of, let's say, 0.8, might look more like this. Okay, so here, if r squared is 1, the line goes perfectly through. R squared of 0, the line has no relationship to the points at all. And r squared in between, it'll be in between. So here, just do this really quick. Okay, so if these are the data points, I haven't drawn a regression line yet. I'm just doing this to emphasize their y coordinates. So all of our data points, what you do is you forget completely about the x coordinate. You take all of your points and you make the x coordinate 0. Then you compute the average of these points. Like here, y bar. Okay, I'm just trying to draw what's the average here of these. And that's it. So this is what you're comparing yourself to. The points just going around the average exactly. That is an r squared equals 0 situation. Now you draw a line and you compute these distances. Here. What the line would have predicted. So for each point, you find its closest place to the line and figure out what your prediction would have been. And then you find the average of these. Well, it's not really the average. These are the yi's. So that's y1. This is y hat. That's why these are the hats, because they're the ones that you would have predicted. Or otherwise the residuals, or the error, with respect to this line. It's 4, y5. Okay? And so if you add up all of these, and it's small compared to this distance, which is just, if you take the average of all these, then which one explains the variance of the data? The variance of the data is this. It's the distance from the points to the average. The average squared distance away from the average. The average here is y bar. If you add up and square all of these red lines, going from the points up to the average, and you square it, that's the variance of the data. So if you explain the variance, it means that you make the variance go down. The variance around the line is smaller than the variance about the mean. Okay, so it's that ratio. This isn't exactly variance because it's not the mean squared distance, it's just the squared distance. The same thing here. This isn't a mean, this is just the sum, but in any case, that's it. That's what an r squared is. Okay, so a very good r squared, quote unquote, explains everything. An r squared of 0 explains nothing. That means that you're exactly the average. Like whatever the average is of the points, that's what you always predict. Just whatever the average is. So you're not predicting really anything useful. Okay, so let's take a 10-minute break. We'll come back at 9:20. And if you have questions about this, I'd like to hear them about the r squared. Thanks. Sorry, I didn't have my mic on. Okay. Sorry about that. Okay, So how do you guys feel about this concept of r squared? Tells you how good the slope is. That's one way of phrasing it. Yeah. It tends to be phrased more like how much of the variance in the data is explained. Maybe I should say. Okay, so I want to go through some more of these. So we've just talked about the r squared. Multiple r is also pretty straightforward. This tells you how strong the linear relationship is. This is just the square root of r squared. Okay, so it also goes between 0 and 1. One nice thing about the y squared, the r squared value compared to, I don't know why they call it multiple r in Excel. I think you can just call it r, not r squared. But r squared, you can interpret it as a percentage. So here, this r squared equal to 0.8 means that 80% of the variation of y values around the mean are explained by the x values. I.e. 80% of the values fit the model. R doesn't have this type of interpretation. Yeah, so that's the nice part about r squared, is you can talk about the percentage of values that fit the model well. The model here is just the line. Okay, this third one, adjusted r squared. That should really be the same number. That's a little odd. Anyway, adjusted r squared is, again, I'll explain it with an example. Adjusted r squared. And in words, adjusted r squared adjusts for the number of terms dependent variables in the model. This is better than r squared if you have more than one x variable. Okay, so that's the description. The equation is not too bad. Excuse me. All right, so what's a good letter for this? Yeah, sometimes it's written like this, okay? An R with the line over it. It's different than an average. I'll give the equation first, and then I'll give an example. This is 1 minus the r squared times n minus 1 over n minus k minus 1. So here, this is the number of data points, and this is number of independent variables. Okay. Okay. Let's say we'll stick to housing. House price. Again, square footage. And whatever. Let's say that the data looks like this, and you draw a line. And you calculate with this line, sorry, not the real number, that the r squared is 0.82. Okay? So far, so good. So I'm going to change the color of this line. All right. Now, let's say that you want to add a third dimension. Okay? And this dimension is I want to choose something stupid. Roof color. That's not a number. I'll say the number of doors. And so now you're predicting the housing prices based on the square footage and the number of doors. So maybe you get another line like this. This is going to actually be a plane now. And this r squared is equal to 0.85. I will ask one of you to explain this to me. But first I'll say it. the more independent variables you add, the higher the R-squared score will be. The R-squared score never decreases when you add more variables. It cannot change, but it will never decrease. It will never, the more independent variables you have, the higher the R-squared value will get. I'll go back up here to remind you what the difference is. Or this is the equation. The regression error over the total squared error. And it's 1 minus that. So when you add more and more and more and more and more independent variables, that will have the effect that this number will never get smaller. It will only, it can only stay the same or get bigger. So even though this has a bigger R-squared value, the number of doors is not a very good predictor of the house price. So this is what the adjusted R-squared does. It's like the R-squared value, except it's scaled by the number of data points you have. And here you're taking away the number of independent variables, and 1 minus that. So if you were to run this model again, using the adjusted R-squared, this adjusted R-squared might be, I don't know, 0.8. And this adjusted R-squared, when you run it just with the number of doors, this might be, 0.4. Something like that. Which means that you should throw out this variable. This adjusted R-squared is too small. This adjusted R-squared doesn't change that much. And so you should just keep this one square footage as the predictor. If you think about this equation for a bit, it will maybe make more sense. Partly it depends on the number of points you have. Here, if you have more and more and more and more and more and more and more points, and you have, then that's going to decrease this this adjusted R-squared value. And if you increase the number of independent variables, that will make this number in the denominator get smaller, especially if the number of variables that you have starts to approach the number of your data points. This is going to get smaller and smaller. This denominator being smaller and smaller makes this bigger and bigger. And so when you subtract that from 1, you'll get a smaller number. Okay. So that's the adjusted R-squared. And the reason why it's better to use the adjusted R-squared if you have more than one X variable, because it can help you avoid adding in kind of trash independent variables. Okay, so how about Afafta here? You got a mic? F off to here. No F off to here. All right. How about Jen?
Yes, I'm here.
Hey. So I just want to ask, when you add more and more and more independent variables, why would that never make the r squared go down in value?
I'm not sure, honestly.
Okay, well, take a look at this equation. If you add more independent variables, is this denominator going to change at all?
No.
Correct. So think of it like a constant. Here, if you add more explanatory variables, could this go down?
Is the explanatory variables the same as the independent variables?
Yes, yes. I'm sorry. Yes, they're the same.
Okay. I don't think so.
You don't think it can go down? Okay, let me ask a different question. This is sort of a different look on it that I actually kind of prefer. Maybe I should have started with it. I did kind of mention it earlier, but I'll mention it again. Y equals m1x plus b. Y equals m2x squared plus m1x plus b. So, with these two models, is there any type of data that you could have where this equation on top would be a better predictor than the one on the bottom?
Oh, I'm sorry. I think I got cut out. Can you repeat that last part?
Sure. Is there any way that this equation on the top could be a better model for the data or have a lower error with the data than this equation on the bottom?
I don't know.
Okay. So the idea here is that this thing on the bottom is strictly more powerful. Because one, it has the x squared term, and so that gives you another thing to play around with. But let's say that the x squared term isn't important. Then you could always, because remember with linear regression, what you're solving for are these m's and the b's. That's what you're trying to find. So if the x squared term isn't needed, you could make this equal to 0. And now the top and the bottom are the same.
Oh, okay, that makes sense.
Yeah, so you can keep adding more and more and more stuff here, with their own m's, I don't know, m4, m100, 1,000, whatever. And you could always turn these off by just making them 0. So, but when you add more and more of these terms, you could be accidentally matching some noise in the data. Like maybe that it's just, I don't know, like if you have two identical houses, one might sell for a little bit less than the other. And like there's no reason for it. It's just sort of a random thing. So if you add more and more and more and more terms, then your model can only do a better job of predicting, but it might be predicting noise. And so, using the word better here isn't quite right. Better in the sense that it has a lower error, but when you try to use it on future predictions, it performs worse. Here's another quick example of that, just because I think sometimes having visual things is nice. Okay, that could be one hypothesis. This could be another one. Okay, same data, but this model here has a bunch of these variables. And so you could exactly fit your data. But the problem is that what happens if you have, a point here that you want to predict? This model on the right, not only does it look cleaner, but it could also be doing a better job of predicting what this x value should be, or what the y value should be for this. Where this one, you're going to be, you could be totally off. This is called overfitting. Actually, I think I have a good, yeah, that's a good one. Here's another example of that just Googled really quick. So this black line is said to be a better predictor than the green line. The green line is matching all of the data perfectly, but it somehow seems like it's, this red point, yeah, the black line makes an error on it, but there's a better trend here. Maybe some of these points are outliers, or they were just labeled wrong, or something. Okay, so coming back here, you already said that this here is a constant, basically, because this value doesn't change when you add more independent variables. This value, though, the y hat, that's your predicted value according to the data that you already have. So if you add more and more and more and more and more independent variables, what's going to happen to this number on top?
Would it also change because you're changing the amount of independent variables?
Yeah. So are the y hats and the y i's going to get closer together or further apart if you add more and more variables?
Would they get further apart?
Here they would actually get closer together. So this yi is the data that you're training on, not the data that you're predicting. When you predict, you're trying to use your model on things that you haven't seen before. This yi is data that you have seen before. The y hat is how close your model comes to these training points. So here on the right, the model gets really, really close to all of the training points. So the y's and the y hats are very, very close together. Where on the left, the y's and the y hats are further apart. For example, on this data point, here, its y hat is this value. And the real y is this. So this would be yi hat, and this is yi. Yi is the true y in your training data. Y hat is your prediction. So here, the predictions are kind of far away.
Okay.
Here, on the same points,
Is the prediction like the predictions are the things that are on the line?
Yes, yes.
Okay.
Okay. So this value will get smaller. The error in the predicted y. So if this number gets smaller on top, and this number here stays the same on the bottom, then what happens to the whole right-hand side? Does it get bigger or smaller?
Would it get bigger?
The number on the top is getting smaller. The number on the bottom is staying the same.
Oh, so then it would get larger.
Smaller.
Okay.
So, 10 over 100 versus 8 over 100. So the number on the bottom is staying the same. The number on the top is getting smaller. So the whole thing gets, 8 100ths is smaller than 10 100ths, right?
Yeah.
Okay. So now what happens if you take 1 minus that?
If the number is larger at the top, then the overall number would be smaller.
Good. Yeah. So when you add more independent variables, you're making this number on top go smaller. And when you take 1 minus this ratio, then that whole thing gets bigger. So that's why when you add more of these random variables, the r squared value can never go down. It can only go up. Make sense?
Yeah, that makes sense.
Okay, good. And thank you very much, Jen. So that is the adjusted r squared, the r squared multiple r standard error. This is just the sorry, I hate what Excel labels stuff as. Say that's just the square root. Oh no. Okay. Yes. The standard error. This is also not something I want to go that much into. This is related to variance. It's an estimation of variance, but I don't think that this is the same variance as what we've talked about. Where is it? Here. So here there's also variance, and that would be nice if it were talking about that type of variance. It's talking about another type of variance, which I don't really see it being that useful. It's sort of an indication on how much you should maybe rely on the adjusted r squared versus the r squared. But I think if you already know the r squared and the adjusted r squared, it's clear enough. You don't need this thing. Okay, so that's it for today's class. Try to play some with Excel over the weekend. No homework assigned today, so try to relax a bit. And if you have questions, issues, whatever, please email me. I'll get back to you over the weekend. And otherwise, we'll pick up more stuff from next Tuesday. So, all right. Thanks, guys.